Good morning, chemistry team. Your chemistry coach is coming at you with some electrochemistry, getting into some new stuff. So you could count this as video number 1 for electrochemistry or video number 5, depending if you include the 4 review videos I put up, because this is all about redox reactions, baby. Electrochemistry is the study of the electron flow that occurs in a redox reaction. So I'm not going to review here. So if you're a little rusty, and a lot of students have trouble with redox, go back to last semester. I put up a bunch of videos. The first 4 videos are reviewing reduction and oxidation reactions outside of solution, and then what happens when they're in solution. What are reducing agents? What are oxidizing agents? Put a video on the redox table, which isn't critical for this chapter, but it's nice to know how to predict products from redox reactions in solution. Pretty tough to do, hard to do by inspection, but not necessary to do electrochemistry because they're going to give you all of them in this. And then the half reaction method, review that for balancing redox reactions that occur in aqueous solution. Can't do those by inspection. Pretty involved process, several ways to do it. Depends if it's in basic or acidic solution. Most of that won't be necessary for this particular chapter on electrochemistry, because they will give you the products and give you what's called the half reaction. But we have to remember how to combine those half reactions to get an overall redox reaction. So review that if you're a little rusty on here. But again, we're just studying the electron flow. That's all redox is electrons going boop, just like acid-base reaction. The proton, the H+, goes from the acid to the base. Doink, that's it. It's not too complicated, right? Redox is the same way, but it's an electron transfer rather than a proton transfer. And the electron goes from the reducing agent, boop, to the oxidizing agent. So a reducing agent is like an acid, just that acids donate protons, reducing agents donate electrons. And so the oxidizing agent resembles the base. Oxidizing agents are electron takers or acceptors, and bases are proton takers or acceptors. So try to keep that in mind. But what wigs people out is because the electron's negatively charged. You lose an electron, but your charge goes up. It's kind of weird when you think about it. So please review that if necessary. And our goal in redox, this is just an intro video, for electrochemistry, is because those electrons are transferring from the reducing agent to the oxidizing agent, can we as chemists utilize that to do something cool with it, right? So electrons are flowing, but if the reducing agent and the oxidizing agent are in contact, because I'm going to actually do some demos on here, I have to grab my goggles before I do that. If they're in contact, the electrons are directly transferring between those. We can't do much with that. But what if we could separate the reducing agent from the oxidizing agent, and then have those electrons transfer along a wire, create a circuit, and then we could bleed off or steal some of that electron flow and use that for interesting things like batteries, right? Making motors run, all that stuff, right? Batteries. Oh, yeah. Oh, if you know what that reaction is to, you're doing awesome. Woohoo! I got my battery shirt on. All right, so let's show you in the next video what happens if we have the reducing and oxidizing agents in contact, and why that doesn't do as much good versus separate them. Gotta keep them separated. All right, let's separate them out and see what advantage we can do with that. All right, gang, so we're going to look at 2 scenarios here. What we're going to do, and I'm going to need my goggles for this one. Let's say we've got a beaker full of a silver +1 ion solution, for example. Maybe some silver nitrate solution, right? So what I did is I put some silver nitrate solution in there, so you can see that clear colorless solution. The nitrate's just a spectator ion, it's not going to do much. And in another beaker, we'll put some zinc nitrate. Ho, ho, ho. So we've got some zinc, which looks like the silver nitrate. And what we're going to do is just a little trick here to see what happens. Let's make sure I get them on the correct side of what you see. And then I got some copper wire. Right on? You recognize copper. So I'm going to put the copper wire in each solution, and that way they're in contact. So silver ions could actually strike the copper wire, and zinc ions could strike the copper wire. If a redox reaction can occur, we'll have electron transfer, right? So does the copper give its electrons to the silver? And does the copper give its electrons to the zinc? That's the question. Does it happen for everything? Is this an automatic process? That's kind of what we're after. So what I'm going to do is I'm going to put these in the solutions here and then take a look at it. It can take a while sometimes. We'll pause the video and then come back in maybe 5 or 10 minutes and see what happens. So let's take this copper. I took some emery cloth or sandpaper and shined up that surface. So this is the silver nitrate solution. So I'm just going to set that in there. And then we'll take a look at it in a little bit. And I'm going to do the same thing with the zinc solution. I'm going to set the copper wire in there. And so it might take a while, but I don't know if you can see the copper here in the silver. Can you see the copper that's in the copper wire inside the solution there? It's already plating out, right? Can you see that? Can you see the silver on it? And in the zinc solution, nothing's changed. Boy, that's happening already. So we'll talk about it and then come back, and it looks really cool. So you can see the silver is, solid silver is plating out on the copper wire inside that solution there. Boy, that's neat. Look at that. Oh, that's pure silver, baby. And in the zinc, diddly squat's happening in the zinc solution. So for some reason, this reaction's occurring, this one is not. Why is that? And they're in direct contact. So let's complete this. Copper's donating electrons over, but copper's going to form a +2. So we're going to get a copper 2 ion plus solid silver. And you can see the solid silver plating out there. Right? You can see that silver plating out. Look at that. Isn't that beautiful? I love silver. It's my favorite element. But this is not happening. So we want to try to understand, why does copper give its electrons to silver but not to zinc? Oh, curious minds want to know. That's why we study electrochemistry, because people back in the past would do this and go, why is that happening? I don't understand. Let's go through our theory a little more. Now what's happening, the silver must be striking the copper to allow the electrons to transfer. So when it hits it, the copper donates an electron to the silver, and then the silver ions plate out as silver atoms, and then the copper atoms, the neutral ones, go out as copper 2 ions. Now, copper 2 ions tend to be blue in solution, so over time, I would expect this to start getting kind of a blue color to it. So we'll let that go for a while. I'll pause this. But this isn't balanced. Now, atomically, it's balanced, but charge is not balanced. It needs to be charge balanced. Right? So you see the copper's losing 2 electrons here. So in order to make this happen, we need to put 2s there. And that's where the half reaction method comes in. We can kind of see this from inspection. That's pretty straightforward. So the copper is giving off 2 electrons. One goes to one silver ion. Another electron goes to another silver ion. So 2 silver atoms plate out as solid silver for every 1 copper 2 ion that goes into solution. And that doesn't happen here. For some reason, when the zinc ions hit the copper, it doesn't pull those electrons away. Now, this doesn't do us any good if we want to perform any kind of work with this. If we want to extract the electrons out and store it in a battery, run some machine or something like that, this won't work because it's directly attacking, right? So the electrons are directly going from the atoms to the ions. We can't extract that out. So what we want to do is separate the silver from the copper. And if we look on this, let's look at the oxidizing and reducing agents. The silver is being reduced, so this is my reducer. And the silver is my oxidizer, if I could spell right. So the silver ion is causing the copper to be oxidized. The copper is causing the silver to be reduced. So we've got the reducer or reducing agent and the oxidizer or oxidizing agent. We want to separate those so we can extract that out. So what we'll do is build a little battery, not a battery, a little called a galvanic cell or electrolytic cell. Well, let me pause it. We'll wait a few minutes and see if we get more cool silver on this and if that solution starts turning blue. So I'll be back in a few minutes, my friends. Hey, I feel while that reaction is running, we can go ahead and do something real quick here. This is what you're going to be doing a lot in this electrochemistry chapter, is figuring out, here's this reaction that's occurring, this redox reaction, can we break it down into its two half reactions, the reduction part, the oxidation part, and look at the electron flow individually? That's what's great about half cells or half reactions, is you can see the electrons. You can't see them in the overall equation. So we know that the silver ion was reducing with the copper because we can see the silver plating out there, right? Can you see? You can actually see some of the blue forming from the copper plus 2 ions. See that crystalline silver? Oh, it's so gorgeous. I'll keep pulling that up periodically. And then the zinc solution. Squat! Diddly squat. So what I did is I took the reaction that occurred, and I got just doing the net ionic equations, just leaving the nitrate ions out. So the silver ions are gaining an electron to go to solid silver. That is the reduction half reaction, where the silver ions are going down in oxidation number. Whereas the copper ions are losing 2 electrons and forming copper plus 2 ions. So that's the oxidation half reaction. So you can see the electron loss in the oxidation and the electron gain in the reduction. But the total number of electrons lost must equal those gained. So when I add these 2 half reactions together, you have to realize I need to multiply this by 2 so I can get 2 electrons there. So this is reviewed in one of the videos, but we will be providing you the half reactions in electrochemistry. You just have to know how to add them together. So let's add these 2 together. Let's multiply everything by 2. So I'm going to get 2 silver ions plus 2 electrons. Let's add the copper. So everything on the left-hand side. On the right-hand side, I'm going to have 2 silver plus copper ions. Plus 2 electrons. And then you can see the electrons on both sides. Those cancel out. Now in some more complicated ones, you might see hydrogen or hydronium ions cancel out, water molecules cancel out. And so we'll get this this simplified equation. You can kind of see it in your head. But I'm just spouting off so we can see the blue color a little better in our demo there. And then what we're going to do is we're going to show you how to separate these 2 half reactions so we can extract the electrons from them. So here's our overall simplified equation that we wrote earlier. But you can now see the 2 separate half reactions. Easy peasy. That is the reaction that's occurring in this beaker right there. Yeah. And that's just going to continue. And again, hopefully you can see it's starting to turn this little faint blue color from the copper 2 ions in solution. You can definitely see the silver growing on there. Very cool stuff. But how do we, this is useless for us. I can't store electrons in a battery or run a motor off of that. So what I'm going to do now is I'm going to take the copper and separate it from the solution. Now I'm not going to do the silver one, but what we're going to do now is we're going to take 2 beakers and separate them into what are called half cells. So this one, I'm going to put a solution in here, and here I've got a piece of copper bent over the side. This one, I've got a piece of zinc, and I'm going to separate these, connect them with wires, and create a circuit where I can extract the electron flow from that, called a galvanic cell. Kind of fun little stuff to do. All right, I'm going to erase this board, and let's show you what happens when we separate them and do a galvanic cell. All right, a couple terms for you guys. When we physically separate the reducing agent from the oxidizing agent, like a scenario like this, now we'll put it piecemeal together. We'll make it and then draw it. If the reducer or reducing agent and the oxidizer or oxidizing agent are physically separated, we create what's called an electrochemical cell. Now, those have 2 different names depending on whether it's spontaneous or not. Like the 2 that we had, the silver ion plus the copper was spontaneous. The zinc ion plus the copper was not spontaneous. So we're going to name those differently because one we can use, the other one is dumb if we want to get any work out of it. A galvanic, or sometimes you'll hear people call them voltaic cells, are spontaneous in the forward direction as written, right? So, I wonder if we're going to connect spontaneity from thermodynamics with delta G values to spontaneity in electrochemistry. We're going to measure the tendency for those electrons to flow with what's called a cell potential, right? So that's going to kind of relate a little bit to the delta G. Can you see equations coming? Connecting these two chapters. You thought thermo was bad. Now we're going to mix it up with electrochemistry. So we have spontaneous electron flow in a galvanic or voltaic cell from the reducing agent to the oxidizing agent. We're going to call those something a little bit different when we do them in the cell. We're going to have what's called an anode and a cathode, and we'll explain those in a little bit. So we can extract those electrons and perform work. Like I said, stored in a battery, run a motor, whatever you want to do. If it's not spontaneous as written, we call that an electrolytic cell. Doesn't mean we can't use it. It's just that it's not going to go on its own, so it needs a little help. So we can just plug it into a wall socket, shoot some electrical current in there, and then force a non-spontaneous process to go, but it requires external help. Right? So like recharging a rechargeable battery, right? When it runs out of juice in the spontaneous direction, you just plug it in the wall, zap the current back in there, throw the electrons in, and boop, reverse the reaction so the non-spontaneous process can go. So let's draw some pictures of what happens when we physically separate these and then show you what it looks like in real life. Hey, there was a good, what was it, Breaking Bad? I think it was, I keep wanting to say Breaking Benjamin, but I think there was a good one in Breaking Bad where they're stuck in this camper or something like that, and he needed to make some energy, and he actually makes a galvanic cell. Really cool stuff. All right, gang, here's the last time we're going to hold these up. Yeah, you can see it now. So you can see the one with the, on the copper wire, you see the silver planted out, and you see the copper 2 ions giving that blue color to the solution. And then the zinc one here, nothing happened. You can still see the copper. You can see the zinc still there. There's no blue at all. So definitely spontaneous for this one. Non-spontaneous for that one. Oh, I love that silver. It's so beautiful. Nice. All right. Now let's separate these. And instead of the silver one, let's do a one where we have like a zinc nitrate solution and a copper nitrate solution. And we just ignore the nitrate. And then we're going to have a solid piece of zinc here and a solid piece of copper here. So it's going to look like this. So here's a beaker with some zinc, right? We're going to call that an electrode. And here we got the copper. So that's the electrode for the copper. And then we're going to keep these separated. And we're going to connect them by a wire with a voltmeter and then what's called a salt bridge to complete the circuit. I'll show you what that looks like physically in a second. But here's how we're going to draw this galvanic cell diagram. Galvanic because it's spontaneous. So here's this beaker, right, with our zinc hooked around. Here's this beaker with our copper hooked around there, right? So my beaker's a little bigger on the board. We're going to connect these together with some alligator clips. So I'm going to hook those onto the electrodes with these wires. This is my voltmeter, so that's going to measure the voltage, which is the potential difference, the driving force for those electrons to go from the reducing agent to the oxidizing agent. So this will be my reducing agent. The oxidation half reaction we usually put on the left-hand side, and the reduction half reaction we put on the right-hand side. So for the oxidation half reaction, we're going to see that the zinc solid is giving off electrons. And those electrons build up on the surface, and they can travel along a wire through the voltmeter to the other electrode, the copper wire. So they're going to start here and end there. We always just kind of by specification put the electron source here, right? And that zinc electrode we call the anode. Anode oxidation. See, they both start with vowels. So oxidation occurs at the anode. That's where it's giving off electrons. They travel through. Now those electrons will build up on this copper, and the copper can shoot off into solution in this scenario, right? Oh, I think I got my arrow backwards here. Hold on. Boop, bloop, bloop. That wouldn't have made a whole lot of sense. There we go. So as the zinc loses electrons, it becomes an ion and spits off into solution. The electrons travel around, build up on the surface of the copper. Copper 2 ions can smack into that solid copper. So copper 2 ions in solution will hit that, pick up those electrons that came from the anode, and then plate out as solid copper. Right? So we're producing positive ions here, because we're losing electrons. We're losing positive ions here because we're gaining electrons. This is a reduction half reaction, and we call that the cathode. The cathode is where reduction occurs. Anode is where oxidation occurs. Cathode is where reduction occurs. The only way to keep these flowing, we got to connect the circuit, is because in the solution, ions are flowing. In the wire, the electrons are flowing, the charge flows. So we're going to connect with what's called a salt bridge. So I have a very high concentration of potassium nitrate solution with these little cotton plugs. And I'm going to dip this upside down into the two separated beakers like an on-off switch. So I can flip that upside down, pop that in there, and that turns the circuit on. It's my on-off switch with a salt bridge. So it's just usually just an inverted glass tube with some porous plugs. And what happens, the nitrate, the anions in the salt bridge flow towards the anode because we're building up zinc ions. So it's becoming too positive, and it has to remain electrically neutral. So for every zinc ion that forms here at the anode half cell, 2 nitrate ions will flow in and keep it electrically neutral. Over in the cathode half cell, for every copper 2 ion that plates out as a solid, we're losing 2 positive charges. Right? So it's becoming too negative. So the potassium ions will flow in to counteract that. That's why you can't have any bubbles in that salt bridge, right? Because we can't have any air gaps in there. Those ions need to flow. So for every copper 2 ion that plates out, 2 potassium ions come in to maintain electrical balance. So this is a galvanic cell diagram. A lot of people just call it galvanic. If I say draw the galvanic cell or voltaic cell, boop, means it's spontaneous. And then that voltmeter will read a particular value. So what I'm going to do is I'm going to put this system together. So I'm going to put some zinc nitrate in here. Concentration doesn't matter at this point. If we're at standard conditions, it'd be 1 molar. We'll probably do 0.1 molar. Not important at this point. I'll put some copper 2 nitrate solution in here. I'm going to connect my wires, connect my voltmeter, and let's do a reading on it. So it's going to take me a minute to set this up. I will be right back so you can study a galvanic or voltaic cell diagram. So if I ask you to do this on exam, I'm looking for all of this. I don't really need the 2 half reactions, but I want you to label the electrodes as anode and cathode. I want you to label which way the electrons flow, always from the anode to the cathode. I want you to draw the salt bridge and how the cations and anions flow to maintain electrical balance. And I want you to draw these little arrows to show that the zinc solid atoms are becoming zinc ions, and at the cathode, the copper ions are picking up electrons when they strike the electrode, becoming neutral copper atoms. So let me connect my voltmeter, see if I can get this going.